Welcome, cosmic explorers, to the realm of slumber and science. It's wonderful you've journeyed to this place. Perhaps a demanding day has just concluded, or maybe you're among those who find tranquility in profound contemplation and the universe's grand enigmas, rather than the familiar count of woolly jumpers. Regardless, this night's expedition is crafted for you. You need only surrender to repose. Allow your thoughts to unfurl, your breath to deepen, and your body to become as light as if gravity's grip had gently loosened. For tonight, our gaze extends beyond mere star observation. We're embarking on a voyage through our cosmic home, the Milky Way. It's an immense spiral of celestial bodies, interstellar dust and unseen matter, rotating serenely through the expanse for over 13 billion years. Yet, beneath its breathtaking facade, profound mysteries reside. Wayward stars, unseen forces, and ancient relics that challenge our very understanding. We will traverse its spiral pathways and delve into its concealed heart, from cataclysmic mergers to stars that predate the galaxy itself. You will learn of ravenous black holes, stellar birthing grounds, and the ongoing, unfinished saga of a galaxy perpetually evolving. Some of what you encounter this evening may astonish you, or at the very least ignite a spark of wonder as you drift into dream. And before we commence, if these tranquil, inquisitive journeys offer solace or a peaceful conclusion to your day, consider bestowing a like and subscribing to this channel. It aids other seekers of calm in finding their way here as well, one slumbering soul at a time. Now, let our exploration begin. The Milky Way has already embraced and absorbed other galaxies, and this cosmic embrace will occur again. Our galaxy may seem like an unshakable sanctuary, but it is fundamentally a construct of shattered celestial bodies. Over eons, the Milky Way has assimilated smaller galactic entities, drawing them inward, dismantling them, and dispersing their stellar components into tidal streams that gracefully encircle its disk. One such entity, the Sagittarius dwarf galaxy, is currently being stretched and pulled apart. Meanwhile, far off in the nocturnal panorama, the Andromeda galaxy is steadily drawing nearer. In approximately 4.5 billion years, these two majestic spirals will converge in a grand cosmic collision. While direct stellar impacts are exceedingly rare, the structural integrity of both galaxies will be irrevocably altered, merging into a new, expansive, and tranquil form. Indeed, even galaxies are not immutable. They transform, collide, and are reborn. Some stars within the Milky Way are older than the galaxy itself. Not every star illuminating our sky originated here. Certain halo stars, characterized by their ancient metal-poor composition and their journey along elongated, inclined trajectories, appear to have formed even before the Milky Way had fully coalesced into its current shape. Astronomers posit that these stars may have originated in smaller primordial galaxies that merged with our own eons ago. Their elemental signatures, exhibiting a scarcity of heavier elements, suggest they were forged in the universe's nascent stages, shortly after the Big Bang. They journey slowly, high above the galactic plane, akin to ancient spirits from an era preceding organized spirals. Within their faint radiance, we perceive a universe that was younger, more untamed, and still in the process of becoming. Our solar system traverses the Milky Way's core at a staggering speed exceeding 828,000 kilometers per hour, equivalent to over 230 kilometers every second. Yet, it still requires approximately 225 million Earth years to complete a single circuit around the galaxy. This celestial circuit is termed a galactic year. Measured in Earth time, our solar system has completed only about 20 such circuits since its formation. When the earliest dinosaurs roamed the Earth, our solar system occupied a vastly different position within the galaxy. The stars we observe tonight were not always in our vicinity, nor will they remain so indefinitely. All is in perpetual motion, silently, gradually, eternally. Even as we rest, our planet spins. Our moon orbits, and our entire solar system glides onward through a galaxy in constant flux. The galaxy continues to expand. Although the Milky Way is ancient, its formation is not yet complete. Even now, it persistently accrues matter. Gas from the intergalactic medium, stars from captured dwarf galaxies, and filaments of dark matter that nourish its halo. Its growth is not analogous to biological life, but rather to a gravitational structure deepening over time. Some of this expansion occurs unobtrusively through the absorption of ambient clouds. At other junctures, it involves significant disruption as satellite galaxies are dismantled, their stars flung across the heavens. The galaxy you inhabit today is not the same one observed by the dinosaurs, and the one your distant descendants will know could be even more expansive, woven from the remnants of countless smaller worlds. We lack a definitive count of the Milky Way's spiral arms. It seems a fundamental aspect of our galactic home that we should know. How many arms emanate from our galaxy's centre? However, from our vantage point deep within the disk, discerning the complete structure is challenging. Obscuring dust clouds impede our view of distant regions. Stars blend into one another. For many decades, astronomers theorized the existence of 4 major spiral arms. More recent observations suggest fewer, or that the arms exhibit a far more intricate twisting and branching pattern than initially conceived. Some fade into fragmented trails, others curl in unexpected ways. The Milky Way may not be a neat pinwheel at all, but rather a dynamic, layered swirl of stars shaped by forces we are still endeavouring to fully comprehend. Rogue stars are propelled from the core. While most stars drift placidly through the galaxy, a select few are ejected at astonishing velocities, attaining speed sufficient to entirely escape the Milky Way's gravitational pull. These are known as hypervelocity stars. Some originate from binary star systems that have been disrupted by the supermassive black hole residing at the galaxy's centre. When one star plunges into the singularity, its companion is flung outward, propelled into the void at speeds exceeding 1 million kilometers per hour. These errant stars journey in solitude, far removed from the galactic plane, resembling incandescent comets with no fixed destination. They serve as a stark reminder that even within a system governed by gravity, moments of violent release can occur, subtle expulsions that send stars hurtling into the interstellar night. The Milky Way and Andromeda are on a collision course. High above the horizon, the Andromeda galaxy appears as a faint ethereal smudge to the unaided eye, a spiral remarkably similar to our own, situated over 2 million light-years distant. Yet, it steadily advances towards us. In approximately 4.5 billion years, the Milky Way and Andromeda will collide. This encounter will not be violent in the conventional sense. Stars are too widely dispersed to directly impact one another. However, their gravitational forces will contort both galaxies into elongated, arcing structures. Tidal tails will unfurl outwards. Black holes may spiral in unison, and after billions of years, these two galaxies will coalesce into a single, grander entity. It will be a slow, elegant cosmic ballet, the future of our celestial abode etched across the tapestry of stars. Some stars orbit in reverse. The majority of stars within the Milky Way trace orbits around the galactic centre in a generally consistent direction. However, not all adhere to this pattern. Certain stars, particularly those situated in the outer halo, exhibit retrograde motion, orbiting in opposition to the galaxy's primary rotational flow. These stars likely originated elsewhere, born in dwarf galaxies that were subsequently absorbed into our own. Their reverse trajectory is a silent testament to their foreign genesis. It is as if the galaxy preserves ancient memories within its celestial dance, narratives of past mergers and cosmic encounters imprinted not in light, but in the slow, patient rotation of stars against the dominant current. The Milky Way may have consumed dozens of dwarf galaxies. It has not achieved its current state in isolation. It has absorbed. Small galaxies, faint companions, have drifted too close, been ensnared by its gravitational pull, and slowly disintegrated. Their stellar constituents are now integrated into our halo, disk, or stellar streams. Astronomers have identified numerous such mergers by scrutinizing stellar movements and compositions. One particularly significant event, the Gaia-Enceladus merger, contributed a substantial number of stars and may have profoundly reshaped the galaxy's nascent structure. The Milky Way is not a pristine spiral. It is a composite creation, fashioned from quiet collisions and stitched together from the fragmented remains of numerous smaller celestial bodies. The elemental composition of stars offers clues to their origins. Each star carries a unique elemental signature, a pattern of elements imprinted at the moment of its birth. By examining these signatures, astronomers can reconstruct a star's history. Some stars are rich in heavy elements such as iron and calcium, indicating their formation in dense, metal-rich environments. Others are composed almost entirely of hydrogen and helium, suggesting they were born when the universe was considerably younger. These compositional disparities enable scientists to categorize stars into families, uncover ancient mergers, and reconstruct the concealed narrative of the Milky Way's evolution. In this manner, chemistry acts as a temporal conduit, allowing us to decipher a star's past as if reading an ancient poem written in starlight. The night sky is adorned with stellar streams originating from galaxies that have been torn apart. Across the celestial sphere, delicate ribbons of stars stretch in arcs and curves, subtle yet unmistakable when precisely mapped. These are stellar streams, the vestiges of smaller galaxies that strayed too close to the Milky Way and were subsequently dismembered. As they orbit, their stars are dispersed throughout space by tidal forces, forming long, ethereal trails that trace their former trajectories. Some encircle the galaxy like spectral halos, others plunge towards its core. These streams serve as tangible evidence of past collisions, quiet mergers that have sculpted the Milky Way over billions of years. The galaxy, much like a venerable tree, displays the rings of its history in every luminous filament. The Milky Way is warped. Our galaxy does not lie flat in a perfect spiral formation. Its disk bends subtly upwards on one side and downwards on the other, creating a graceful, undulating wave across the starscape. This subtle curvature remained imperceptible until radio telescopes were employed to map the hydrogen gas that extends far beyond the visible starlight. Astronomers hypothesize that this distortion may be caused by the gravitational influence of satellite galaxies gently tugging at the Milky Way's extremities, or perhaps by concentrations of dark matter subtly bending the structure from beneath. Akin to ripples on a colossal spinning disk, this warp demonstrates that even galaxies are in perpetual motion, subject to bending, flexing, and transformation in response to unseen forces. From a distance, the Milky Way might appear to be engaged in a slow, graceful, celestial dance. We can perceive only approximately 0.00003% of the Milky Way with our unaided eyes. Under a clear, unpolluted night sky, far from urban illumination, one might observe a few thousand stars. To the human eye, this appears as an oceanic expanse of light, yet it represents but a mere droplet. The Milky Way encompasses over 100 billion stars. The vast majority remain hidden from our view. Some are obscured by dense curtains of dust. Others are too faint or too distant for our visual acuity to detect. The faint, luminous streak of the Milky Way that traverses the sky on moonless nights is merely the faintest whisper of its totality. We reside within a colossal river of starlight, yet almost all of it remains concealed from us, too immense to be comprehended from our internal perspective. Stars orbit the galaxy at varying velocities. Unlike planets within a solar system, which follow precise orbits around their star, stars within the Milky Way exhibit greater freedom of movement. Some accelerate rapidly in the inner regions, while others drift languidly along the periphery. This disparity in speed is the genesis of spiral arms. They are not solid constructs, but rather emergent patterns, akin to slow-moving traffic jams of stars and gas traversing space. As these density waves propagate, they stimulate the formation of new stars, igniting the arms in swirling coronas of blue and white. Our own sun participates in this grand circulation, weaving in and out of these patterns over cosmic timescales. The galaxy is not a rigid mechanism, it is a current, and we are carried within its flow. The galaxy remains cohesive due to a phenomenon we cannot perceive. By all conventional understanding, the Milky Way should not exist. Based on our measurable parameters of stars, dust and gas, the outer extremities of the galaxy are rotating with excessive speed. They should be flung outwards, dispersed like leaves in a tempest, yet they remain bound. The explanation lies in dark matter. This enigmatic substance neither shines, reflects, nor emits any form of light. However, it exerts gravitational influence, and its sheer abundance far outweighs all visible matter within the galaxy. We remain uncertain about the true nature of dark matter, but its indispensable role in preventing the Milky Way from disintegrating is undeniable. It is the invisible scaffolding that maintains the galaxy's structural integrity. A supermassive black hole resides at its core. At the very heart of the Milky Way lies an immense black hole, a point of singular gravitational intensity known as Sagittarius A. It possesses a mass exceeding 4 million times that of our Sun, yet it occupies a spatial volume smaller than the orbit of Mercury. We cannot observe it directly, but we have meticulously tracked the trajectories of nearby stars as they whip around it at extraordinary speeds, tracing unseen ellipses through the void. Periodically, gas and dust descend into its gravitational maw, flaring with X-ray emissions as they spiral towards the event horizon. At present, Sagittarius A rests in a quiescent state. However, in its ancient past, it may have blazed as a quasar, illuminating the galaxy from within. It acts as the silent conductor of the Milky Way's central rhythm, drawing stars into a slow, inexorable celestial waltz. The Milky Way possesses a peanut-shaped central bulge. When astronomers mapped the galaxy's core, they uncovered an unexpected revelation. The central bulge is not a smooth, spherical concentration of stars, but rather a three-dimensional structure resembling a peanut. Viewed from the side, it expands in its midsection and tapers at its extremities, akin to a twisting hourglass formed from stars. This peculiar geometry likely originated from the galaxy's central bar, a dense stripe of stars that rotates slowly, buckling and expanding upwards over time. These internal structures are meticulously sculpted by gravity, the cumulative effect of billions of years of motion and the synchronized rhythm of stellar orbits. We inhabit a spiral galaxy, yet its core is imbued with profound complexity. Far from being flat or uniform, it is intricate and vibrantly alive. Stellar nurseries delineate the spiral arms. The spiral arms of the Milky Way are not merely comprised of stars, they are intricately woven from the very cradles of stellar creation. Vast nebulae of hydrogen, dust, and molecular compounds drift through the galaxy. As these clouds traverse the spiral arms, they undergo compression and ignite with the birth of new suns. These regions are designated as stellar nurseries, characterized by their chaotic, luminous, and dynamic nature. Ultraviolet radiation emitted by nascent stars illuminates these clouds, imbuing the arms with radiant hues of blue and silver. These bursts of creation vividly outline the spiral configuration, illuminating the galaxy's curves with a gentle, ethereal fire. Every star, including our own sun, emerged from one of these nebulous wombs eons ago. The Milky Way is enveloped by an extensive halo. Beyond the broad, flat disk of the galaxy lies a far more diffuse structure, a spherical halo encircling the entirety of the Milky Way. This halo contains ancient stars, globular clusters, and prodigious quantities of dark matter. Though largely imperceptible, this halo may contain the majority of the Milky Way's mass. Its stars are sparsely distributed across immense distances, traversing elongated, slow orbits that seldom intersect the disk. The halo also safeguards the remnants of ancient galactic mergers, preserving streams and shells of stars dislodged from smaller galaxies, left behind like cosmic fossils. It represents the galaxy's ancestral memory, serene and dim, yet perpetually in motion, continuously shaping the Milky Way's future form. It contains over 150 globular clusters. Globular clusters stand as some of the most ancient entities within the galaxy. These compact spheres comprise hundreds of thousands of stars densely packed together. They orbit the galactic center within the halo, resembling moths drawn to a distant flame. These clusters exhibit remarkable stability, some dating back over 12 billion years, and many contain stars that predated the Milky Way itself. Their stellar populations are metal-poor, indicating their formation before the universe had synthesized a significant abundance of heavier elements. They function as temporal capsules, safeguarding clues regarding the galaxy's formation, its assimilated constituents, and the conditions prevailing in the early cosmos. These tranquil, golden spheres drift patiently above and below the galactic plane, emanating a soft glow in the darkness. The galaxy is still expanding. Although the Milky Way is ancient, its evolutionary journey is far from complete. Even at this moment, it continues to accumulate material. Gas drawn from the intergalactic medium, stars liberated from captured dwarf galaxies, and streams of dark matter that nourish its encompassing halo. Its growth is not organic, but rather analogous to a gravitational structure deepening and expanding over time. Some of this accretion occurs unobtrusively through the assimilation of ambient cosmic clouds. At other junctures, it involves disruptive processes as satellite galaxies are torn apart, their stellar components scattered across the vastness. Rogue stars are propelled from the core. While most stars drift placidly through the galaxy, a select few are ejected at astonishing velocities, attaining speed sufficient to entirely escape the Milky Way's gravitational pull. These are known as hypervelocity stars. Some originate from binary star systems that have been disrupted by the supermassive black hole residing at the galaxy's center. These errant stars journey in solitude, far removed from the galactic plane, resembling incandescent comets with no fixed destination, hurtling into the intergalactic night. Star formation is diminishing. In ages past, the Milky Way was a more dynamic entity, teeming with newly formed stars born from dense collapsing nebulae. However, in recent cosmic epochs, the rate of stellar genesis has slowed. While gas remains available, a significant portion is now thinly dispersed, heated, or locked in configurations that resist gravitational collapse. The galaxy is not ceasing its star-making endeavours, but its pace has moderated. Astronomers estimate that the peak of star formation occurred billions of years ago, and its intensity has been in decline ever since. This does not portend an imminent end, but rather signifies that we inhabit a quieter phase of galactic evolution. A mature spiral galaxy glowing gently in its middle age, still capable of stellar creation, but no longer driven by the same urgency. Some stars formed before the Milky Way possessed a disk. The disk, the broad, flattened spiral structure we commonly associate with the Milky Way, coalesced gradually over immense periods. However, some of the stars within our galaxy predate the disk itself. These ancient stars are primarily located in the halo, or the thick disk, and they formed during the galaxy's formative stages, when it was an amorphous collection of stars, gas, and dark matter slowly contracting under gravity. By analysing their elemental composition and orbital patterns, astronomers can glimpse into the era before organised structure, before the emergence of distinct spirals. These stars represent the galaxy's elders, silent witnesses to its genesis and the prolonged, gradual shaping of what we now call home. A galactic year is approximately 225 to 250 million Earth years. As the Sun orbits the Milky Way's centre, it completes a single revolution every few 100 million years. This vast cycle of motion, known as a galactic year, dwarfs all our terrestrial calendars. In the time it takes for the Sun to circumnavigate the galaxy once, continents drift, species emerge and vanish, and entire geological epochs unfold. It is estimated that we are currently roughly halfway through one such orbital period. The last time our solar system occupied this segment of its trajectory, the supercontinent Pangaea was just beginning to fracture, and dinosaurs had not yet appeared. A galactic year signifies the slow, deliberate heartbeat of cosmic time. The Sun has completed fewer than 25 galactic orbits. In its entire existence of 4.6 billion years, the Sun has circled the Milky Way only around 20 times. This number might seem surprisingly low considering its tremendous velocity, approaching 830,000 kilometers per hour. However, the galaxy's sheer vastness and the Sun's extensive orbital path mean each revolution spans hundreds of millions of years. We often perceive stars as ancient and stationary. Yet, our solar system remains relatively young on a galactic scale, a newcomer in a city populated by older, more seasoned suns. We are integral to the galaxy's motion, but still in the nascent stages of its long, winding narrative. The Milky Way's rotation defies Newtonian predictions. According to classical Newtonian physics, stars located farther from the galactic centre should orbit at slower velocities, much like the outer planets move more leisurely around the Sun. However, within the Milky Way, stars in its outer regions orbit with velocities nearly as high as those closer to the centre. This observation contradicts classical expectations. Astronomers attribute this anomaly to dark matter, an invisible, unidentified form of mass that encases the galaxy in a vast halo. Without dark matter, the galaxy would not maintain its structural integrity. With its inclusion, the mathematical models align. The Milky Way rotates as if it were a solid disk, not because we fully comprehend its mechanics, but because an unseen entity is holding it together. The galaxy harbours enormous molecular clouds. Scattered throughout the Milky Way are vast, dark clouds of frigid gas, serving as the raw material for star formation. These molecular clouds, predominantly composed of hydrogen molecules and trace amounts of dust, can span hundreds of light years. Within their cold, dense interiors, gravity gradually draws material together, forming concentrations that collapse to give rise to new stars and planets. Some of these clouds are so colossal and frigid that they completely absorb visible light, appearing as dark voids against the starry backdrop. They are the galaxy's wombs, silent, hidden sanctuaries where the future begins in tranquility, concealed within veils of shadow and gas. Cataclysmic stellar detonations known as supernovae agitate the cosmos like tempests. When colossal suns reach the final stages of their existence, they erupt in spectacular explosions. These events are so immensely powerful that for a fleeting moment, they can outshine entire constellations. These spectacular bursts of energy don't merely extinguish stellar lives, they also initiate creation. The shockwaves emanating from these supernovae propagate through the vast expanse of interstellar space, compressing nearby gas clouds and catalyzing the birth of new stellar generations. They infuse the surrounding cosmic environment with weighty elements such as iron and gold, elements meticulously forged within the fiery hearts of dying stars. In this profound manner, supernovae function as cosmic storms within the galactic ecosystem, orchestrating a cycle of agitation, nourishment, and transformation for everything in their vicinity. They represent the galaxy's periods of spectacular upheaval, characterized by destruction, brilliance, and indispensable contribution. Obscuring clouds of cosmic dust conceal vast domains where stars are being born. Our own Milky Way galaxy is teeming with luminescence that remains imperceptible to our eyes. Interstellar dust composed of minuscule particles of carbon, silicon and ice, meanders through the galaxy in intricate formations of clouds and wisps. In the realm of visible light, this dust obscures enormous stretches of space, effectively blotting out the light from distant stars and entire nebulae. Yet, concealed behind this ethereal veil, the ongoing process of star formation continues unabated. Infrared telescopes possess the remarkable capability to penetrate this dusty barrier, revealing glittering stellar nurseries brimming with newly ignited suns. What appears as impenetrable darkness is, in many instances, a nurturing incubator. The dust, though it conceals, is an integral component of this cosmic ballet, absorbing energy, facilitating the cooling of gases, and providing a protective shield for the delicate nascent stages of stellar development. What may seem like mere emptiness is frequently the precursor to something luminous. Drifting through the vastness of the galaxy are clouds of gas devoid of stars. Not every gaseous aggregation is destined to transform into a star. Across the expanse of the Milky Way, astronomers have identified immense frigid clouds that appear poised for gravitational collapse, yet persist in a state of darkness and dormancy. Certain clouds are simply too diffused. Others may maintain their stability through the influence of magnetic fields or internal turbulent forces. These starless clouds float through the galaxy like silent possibilities. They are rich in molecular hydrogen, but remain untouched by the process of nuclear fusion. They might one day ignite and become luminous celestial bodies, or they may drift until external forces tear them asunder, their constituent gases then being recycled into other regions of the cosmos. Within these ethereal clouds, the galaxy seems to hold its breath, perhaps anticipating the opportune moment to spark something entirely new. The Milky Way orchestrates a continuous recycling of matter across successive cosmic generations. Stars are not immutable entities. They experience a life cycle of existence, luminescence, and eventual demise, and in their passing, they return their material constituents to the galactic milieu. Supernovae disperse heavy elements throughout space. Red giant stars shed their outer atmospheric layers. Planetary nebulae gently dissipate outwards into the cosmic void. This enriched material then rejoins the interstellar medium, where it cools, coalesces, and ultimately gives rise to the formation of new stars, planets, and indeed, life itself. Every single atom composing your being has journeyed through this grand cosmic cycle. It was born within a star, subsequently scattered into the interstellar medium, and eventually gathered to form new structures. The Milky Way is not a static tableau, but rather a magnificent engine of perpetual renewal. It breathes in rhythm with its stellar inhabitants, engaging in processes of creation, dissolution, and renewed beginnings. Stars deficient in heavy elements offer profound insights into the early universe. In the lexicon of astronomy, metals encompass any elements heavier than helium, not solely iron or gold. The very first stars to emerge in the universe contained virtually no such elements, as they formed prior to earlier stellar generations having the opportunity to forge and disseminate them. Presently, astronomers actively seek out stars with low, metal content within the galactic halo of the Milky Way. These stars, faint and ancient, preserve the chemical conditions of a bygone era. By scrutinizing their elemental composition, we gain the ability to peer into the primordial past, specifically into the epoch immediately following the Big Bang, a time before galaxies had achieved maturity, and even before the Milky Way itself had fully coalesced into its current form. These celestial bodies are essentially fossils rendered in light. Some stars embark on journeys far from their places of origin. A star's initial birthplace does not invariably dictate its ultimate destiny. Over extended periods, numerous stars gradually drift away from their natal gas clouds, propelled by gravitational interactions, orbital resonances, or the subtle, persistent pull of spiral arms. Certain stars are violently expelled at immense velocities, flung across the galactic disk or even into the halo. Others migrate more gradually, subtly altering their orbital paths inward or outward as they spiral through the galaxy. Even our own Sun is not situated in the exact location where it originally formed. The meticulous tracing of stellar trajectories reveals a Milky Way that is anything but static. It is a dynamic entity, alive with movement, material exchange, and quiet shifts in position. A star's cosmic home may prove to be only a temporary abode. The galaxy's potential zone for harbouring life might extend across tens of thousands of light years. Just as Earth maintains an orbit within a Goldilocks zone around the Sun, a region neither too hot nor too cold to support life, the Milky Way may possess its own analogous galactic habitable zone. This region is hypothesized to exist between the perilous inner core, characterized by intense radiation and gravitational instability, and the sparse, metal-poor outer fringes where planet formation might be more challenging. Somewhere in this intermediate band, conditions are presumed to be stable, with moderate stellar density and an abundance of elements like carbon, oxygen, and iron. Earth is situated within this zone, occupying a quiet orbit in a vast cosmic swirl where life might not be the sole entity to have found a foothold. The spiral arms are not rigid structures. The spiral arms of the Milky Way might appear as permanent fixtures, grand, sweeping lines etched into the galaxy's disk. However, they are not comprised of fixed stars. Instead, they are dynamic patterns, essentially density waves that propagate slowly through the disk, compressing gas and stimulating the formation of new stars as they pass. Stars drift into these arms, shine for a period, and then drift out once more. The spiral structure itself rotates at a different velocity than the individual stars within it, akin to a traffic jam moving along a highway. From a distance, it presents an illusion of form and order. From within, it is a pattern of shifting motion, held together by the fundamental forces of gravity and time, perpetually in flux and always flowing. The Milky Way resonates with cosmic radiation. Beyond the spectrum of visible light, the galaxy emanates with more enigmatic forms of energy. Cosmic rays, which are high-energy particles originating from supernovae and distant galaxies, stream through space and traverse your body every second. X-rays and gamma rays shimmer from dying stars and black holes. Radio waves drift from gas clouds, pulsars, and the faint, cold emissions of hydrogen. These imperceptible emanations reveal phenomena that visible light cannot capture, including the violence, magnetism, and ancient fiery processes still flickering within the galaxy's fundamental structure. When you gaze into the night sky, you're merely observing a narrow slice of the Milky Way's true energetic spectrum. Beneath the visible stars, the galaxy softly hums across a multitude of frequencies and colours, constituting a hidden symphony in the darkness. Enormous gamma-ray lobes extend above and below the galactic centre. Stretching for tens of thousands of light-years above and below the galactic core are two vast ethereal lobes of high-energy light. These structures, known as the Fermi bubbles, were only recently discovered. They radiate in gamma rays, extending outwards like twin balloons from the heart of the Milky Way. The precise cause of their formation remains uncertain. They might be the residual effects of a significant outburst from the central supermassive black hole in the distant past, or they could be indicative of intense star formation that once blazed through the galactic core. Regardless of their origin, these immense structures drift silently through the galaxy, undetectable to the human eye. They serve as potent reminders that the Milky Way harbours a past that remains largely obscured from our comprehension. These are echoes of cosmic violence, wrapped in radiant energy, hovering far above the familiar stars we observe. Our solar system resides in a minor arm, situated between major galactic structures. Our solar system is not located within one of the Milky Way's grand spiral arms. Instead, we occupy a smaller feature known as the Orion Spur, a relatively tranquil stellar lane nestled between the larger Sagittarius and Perseus arms. This region is neither particularly dense nor exceptionally active, and this quietude might be precisely why life has emerged here. In the calm spaces between major galactic thoroughfares, cataclysmic supernova events are less frequent, and radiation storms are less common. This serene corner may have provided the necessary time for life on Earth to originate and evolve. While the galaxy as a whole appears dramatic and luminous from a distance, this quiet spur has offered the tranquility required for complexity to unfold. The Milky Way possesses a bar-shaped central structure. When astronomers direct their observations toward the galactic core using infrared light, they perceive not a perfect circle, but rather a thick, elongated bar of stars traversing the centre, forming a sort of luminous bridge. This bar rotates slowly, and its gravitational influence plays a crucial role in shaping the inner spiral arms. Such barred structures are common among spiral galaxies. They form when stars within the disk begin to drift inward and accumulate along a central axis. Over extended periods, the bar evolves into a stable configuration, agitating gas, stimulating the birth of new stars and channeling material towards the supermassive black hole situated at the galactic centre. It is not merely a shape, but a dynamic engine, actively sculpting the heart of the galaxy from within. This structure is part of a larger cosmic association. The Milky Way does not exist in isolation. It is part of a collective of more than 50 galaxies, collectively known as the Local Group, a relatively small cluster drifting together through space. The two most prominent members of this group are the Milky Way and Andromeda, each accompanied by its own retinue of satellite galaxies. Scattered around these larger galaxies are smaller dwarf galaxies, faint elliptical galaxies, and star-poor galaxies composed almost entirely of dark matter. The Local Group spans a distance exceeding 10 million light-years and is bound together not merely by proximity, but by the fundamental force of gravity. We are part of this cosmic family, characterized by quietude and wide spacing, yet inextricably linked by the invisible threads of shared motion and mutual gravitational attraction. Galaxies within the Local Group are gravitationally bound. Despite their immense distances from one another, the galaxies of the Local Group are not drifting apart. In fact, many are slowly moving towards each other. Gravity orchestrates their movements in a slow-motion ballet, shaping their trajectories across millions of years. Some of the smallest galaxies orbit the Milky Way as if they were moons, tracing looping paths and gradually dissolving into streams of stars. Others drift independently but remain tethered, caught within a web of interconnected motion. Over vast stretches of time, this group is expected to condense. Galaxies may merge, fade from existence, or be absorbed by larger entities. It is not a static arrangement, but a gentle convergence of cosmic islands, a family drawing closer through the passage of time, inertia, and the far-reaching influence of gravity. The galactic disk comprises both a thick and a thin component. From a distance, the Milky Way's disk appears flat. However, upon closer examination, it reveals a layered structure. The thin disk is where our solar system is situated. It is a broad, dense plain populated with young stars, open star clusters, and gas clouds actively undergoing star formation. Above and below this thin disk lies the thick disk, which is older, more diffuse, and possesses a puffier appearance. Stars within the thick disk tend to be older and contain fewer heavy elements. They follow orbits that are more inclined and elliptical, suggesting they formed under different conditions or were significantly perturbed by early galactic collisions. The galaxy's disk is not uniform. It possesses a textured, layered quality, shaped by time, much like sediment settled on the floor of a cosmic ocean. The galaxy's magnetic field permeates the disk. Although invisible to the naked eye, the Milky Way is interwoven with a vast magnetic field that extends across the disk, ascends into the halo, and permeates the interstellar medium. This field is relatively weak by terrestrial standards. However, over galactic distances, it profoundly influences the trajectories of cosmic rays, the collapse of gas clouds, and the flow of matter through space. It aligns with the spiral arms, forms arcs above the galactic plane, and twists into complex loops that defy simple explanations. Studying this magnetic field necessitates the use of radio telescopes and meticulous analysis. Nevertheless, its presence is undeniable. The Milky Way does not merely radiate light, it also possesses a magnetic pulse, a subtle rhythm running through its very structure. The interstellar medium is replete with unseen structures. The space between stars is not an empty void. The interstellar medium, a tenuous mixture of gas, dust, and plasma, permeates the Milky Way like a pervasive fog. To the unaided eye, it is largely invisible. However, when observed with radio and infrared telescopes, it reveals an astonishing level of complexity. It manifests as filaments, bubbles, shock waves, and cold, dense clouds where stars come into being. Supernovae carve vast cavities within it. Stellar winds sculpt it into intricate shapes that ripple across light years. The space between stars is not an absolute void, but rather a dynamic, shifting tapestry of matter and magnetism. It is the quiescent fabric from which galaxies evolve and ultimately life begins to emerge. Cosmic rays constantly stream through us from the galaxy. Every second, high-energy particles, primarily protons and atomic nuclei, pass through your body, having been propelled long ago by exploding stars. These are known as cosmic rays, and they are ubiquitous. They travel at speeds approaching that of light, bending through magnetic fields, ricocheting off gas clouds, and occasionally colliding with atoms in Earth's atmosphere, where they generate showers of secondary particles. While we're largely unaware of them most of the time, they carry profound stories from across the galaxy, bearing witness to ancient supernovae, traces of distant acceleration events, and messages from the violent cosmic furnaces of stars. Even as you remain stationary, the galaxy is subtly communicating through these particles, in silence and in non-luminous rays. The galaxy is not symmetrical, despite how many diagrams depict it as a neat, uniform spiral. The Milky Way is not perfectly balanced. One side of its disk appears thicker than the other. Some spiral arms are more luminous, elongated, or curved than their counterparts. The warping observed in the outer disk is lopsided. Even the number of stars counted in opposite hemispheres shows slight discrepancies. These asymmetries may be attributed to gravitational encounters with other celestial bodies, past galactic mergers, or the influence of unseen dark matter. They serve as a reminder that galaxies, much like living organisms, bear the indelible marks of their histories within their shapes, scars from collisions, wrinkles etched by time, and quirks of uneven growth that lend them unique character and depth. The oldest known star may reside within our galactic halo. Situated high above the galactic plane, drifting through the halo, astronomers have identified a star that may be nearly as ancient as the universe itself. This star contains virtually no elements heavier than helium, a telltale characteristic of stars that formed shortly after the Big Bang, prior to the enrichment of the cosmos by subsequent generations of supernovae. It likely originated more than 13 billion years ago, long before the Milky Way had fully coalesced into its present form. It now burns quietly with a gentle red glow, possessing low mass but an immense historical significance. It is not merely a star. It is a time capsule, a living relic from the universe's earliest dawn. The central region of the galaxy rotates at a faster pace than its outer periphery. In the inner regions of the Milky Way, stars orbit the galactic center at considerably higher velocities than those located farther out. Close to the core, the gravitational pull is more intense, concentrated by the mass of stars, dust, and the supermassive black hole known as Sagittarius A. This intense gravity compels stars to sweep through tighter, faster orbits, completing their revolutions in a mere few million years. Out in the more distant suburbs of the galaxy, such as where our Sun is located, stars orbit more slowly, taking hundreds of millions of years to complete a single revolution. This disparity in rotational speeds creates twisting patterns, elongates the spiral arms, and prevents the galactic disk from behaving as a solid, uniform structure. The galaxy rotates like a colossal wheel, but one whose outer rim lags behind its central hub. Spiral arms are shaped by density waves. The spiral arms of the Milky Way are not static trails of stars. Rather, they are patterns formed by waves of increased density propagating through the galactic disk. As gas and dust encounter these waves, they are compressed, triggering the formation of new stars and illuminating the arms with the brilliance of young, hot stars. These stars eventually drift out of the wave, while new ones form behind them, creating a self-perpetuating illusion of structure. Akin to ripples on a pond or a traffic jam on a highway, these arms are dynamic and in constant motion. From a distance, they appear still. From within, they are a vibrant dance of matter and rhythm sculpted by gravity and time. Stars are born from the slow collapse of cold gas. Within the dim recesses of the Milky Way's spiral arms, star formation commences in silence. Vast clouds of molecular hydrogen, sometimes spanning hundreds of light years, drift through space, chilled to just a few degrees above absolute zero. Within these frigid clouds, gravity gradually asserts its influence. Small regions within the cloud begin to increase in density and commence collapsing under their own weight. As the gas falls inward, it heats up, begins to spin, and flattens into a protoplanetary disk surrounding a central protostar. Over time, the internal pressure and temperature rise until nuclear fusion is ignited, marking the birth of a new star. From the coldest shadows emerge the brightest lights, gently spun into existence by the quiet, inexorable force of gravity. Star clusters can gradually dissipate into the wider galactic field. Many stars do not originate in isolation, but rather in groups. These are tight-knit clusters formed from the same collapsing gas cloud. Bound together by their mutual gravitational attraction, these clusters drift collectively for millions or even billions of years. However, over time, they begin to disperse. Tidal forces exerted by the Milky Way's immense mass, close encounters with other stars, and internal dynamic processes all contribute to pulling these clusters apart. Stars gradually peel away, one by one, until the cluster fades into the general star field of the galaxy. Even our Sun is believed to have been born within a stellar cluster in the distant past. Its sibling stars are now scattered, dimmed, or lost in the haze of immense distances. The galaxy harbours ancient hyper-metal-poor stars. Among the rarest and most precious celestial objects found within the Milky Way are hyper-metal-poor stars. These are stars whose atmospheres contain virtually no elements heavier than helium. Some of these stars exhibit less than 100,000th of the iron content found in our Sun. These stars are believed to be among the very first to form after the initial supernova events, carrying only faint traces of enrichment from a universe still in the process of its own formation. They are extraordinarily ancient, exceptionally pure, and scattered throughout the galactic halo like distant lanterns from the dawn of time. Each one represents a form of relic, a luminous, gravitationally bound signature from a nearly forgotten epoch. Planetary systems form throughout the Milky Way. Planets are not an uncommon feature of the cosmos. They are a natural consequence of the process of star formation. As a new star ignites, a rotating disk of residual gas and dust encircles it. Within this disk, particles begin to adhere to one another, accumulating mass and gradually growing into worlds. Across the Milky Way, planetary systems are a common occurrence. Some are vast, containing gas giants and icy moons. Others are more compact, with rocky planets orbiting closely to dim stars. Some may bear a resemblance to our own solar system, while others might present entirely unexpected characteristics. The galaxy is not merely populated by stars, but also by a multitude of systems, cosmic families, each possessing its own unique equilibrium, orbital path, and inherent potential. Earth is situated near the co-rotation radius. Within the Milky Way, the spiral arms rotate at a different speed than the individual stars comprising them, functioning more like a propagating pattern than a rigid structure. However, there exists a specific distance from the galactic center, known as the co-rotation radius, where the average speed of stars aligns with the rotational speed of the spiral arms themselves. The Sun's orbit is situated close to this boundary. This gentle synchronization of motion may contribute to us avoiding frequent passages through the spiral arms, which are regions characterized by higher stellar density, increased supernova activity, and gravitational disturbances. It is quite possible that we inhabit a more stable neighborhood within the galaxy, shielded not by physical barriers but by orbital resonance. The Sun bobs up and down through the galactic plane. As it orbits the Milky Way, the Sun does not follow a perfectly flat trajectory. Instead, it moves in a gentle, wave-like motion, ascending and descending relative to the galactic plane like a cork bobbing in slow motion. This vertical oscillation occurs over tens of millions of years and is caused by the gravitational pull of the galaxy's overall mass, which alternately attracts and releases the solar system as it progresses. Some researchers have even speculated that this motion might influence cyclical extinction events on Earth, though definitive evidence remains elusive. Nevertheless, it serves as a compelling reminder that even on its steady path around the galactic center, the Sun is not gliding smoothly, but rather swaying softly through space. We do not know the precise nature of dark matter, but we are certain of its existence. Dark matter constitutes the majority of the Milky Way's mass, yet it has never been directly observed. It neither emits nor absorbs light, passing through ordinary matter as if it were not present. However, its gravitational effects are undeniable. It is the force that holds the galaxy together, explains the unexpectedly high rotation speeds of stars, and shapes the formation of large-scale cosmic structures. Without it, the Milky Way would disintegrate. Astronomers detect its presence not by seeing it directly, but by observing its influence on other celestial bodies. It represents the galaxy's hidden framework, invisible, silent, and still one of the most profound mysteries in scientific inquiry. There is more mass located outside the galactic disk than within it. The majority of the Milky Way's visible stars are contained within its flat, luminous disk. However, the bulk of its mass resides elsewhere. The galaxy is enveloped by an enormous dark matter halo that extends far beyond the outermost stars. This luminous halo encircles the galaxy, possessing substantially more heft than the galactic disk. It harbours a sparse population of ancient stars and globular clusters, though its principal mass remains invisible. When we envision the Milky Way, our minds conjure its spiralling arms and stellar plane. Yet this is merely the luminous veneer. The very substance that defines the galaxy, its gravitational influence, its momentum, its vast expanse, is largely concealed, enfolding everything like a silent mantle. The core of the Milky Way may have once blazed as a quasar. Today, the heart of our galaxy appears tranquil, but evidence indicates it was once dramatically more vigorous. The existence of colossal gamma-ray structures like the Fermi bubbles and traces of high-energy light reflected in surrounding nebulae suggest that the supermassive black hole at its centre might have once erupted as a quasar, a dazzlingly violent beacon fueled by infalling matter. Quasars rank among the universe's most luminous objects, outshining entire galaxies. Had the Milky Way once burned with such intensity, it would have presented a strikingly different aspect, a spiral coiled around a blinding nucleus of light. That era has long since passed, but its residual effects persist. The galaxy's architecture undergoes transformations over eons. Galaxies may appear eternal, but they are in perpetual flux. Spiral arms shift. Galactic bars form and dissipate. Gas streams flow inwards and outwards. Stars are born and expire, leaving behind an ever-changing stellar population. Even the shape of the Milky Way's disk, warped, undulating and asymmetrical, is gradually altering. Encounters with dwarf galaxies and dark matter can contort or twist its structure. Over billions of years, the galaxy's silhouette has shifted like a drifting cloud. The Milky Way of today is neither the one that was nor the one that will be. Its beauty resides not in immutability, but in its quiet metamorphosis. Gravitational waves propagate through the galaxy from distant cosmic collisions. Across the cosmos, colossal entities converge, black holes spiral into one another, neutron stars collide, and entire galaxies merge. These cataclysmic events generate gravitational waves, ripples in the very fabric of space-time. Though subtle, some of these waves traverse the Milky Way, momentarily distorting space by minuscule amounts. Their detection is exceedingly challenging, yet observatories such as LIGO and Virgo have already registered several. New initiatives aim to perceive the pervasive background hum of gravitational waves that saturates the universe. Even now, as you rest, space-time itself is in motion, not to a perceptible degree, but enough to inform us that somewhere far off, the universe is undergoing transformation. Certain stars traverse elongated, inclined trajectories. Not all stars circumnavigate the galactic center in neat circular paths. Some follow elongated elliptical orbits, their paths arcing far above and deep below the galactic disk, tilted at peculiar angles relative to the principal plane. These stars likely originate from disparate sources, remnants of dwarf galaxies absorbed by the Milky Way, or survivors of ancient gravitational upheavals. Their orbits serve as clues, three-dimensional maps detailing the galaxy's tumultuous past. By charting their movements, astronomers reconstruct the invisible framework of the Milky Way's mass and historical record. These stars drift like emissaries from disrupted systems, tilted, elongated, yet still tethered to the galactic whole. The Milky Way emits neutrinos that we can barely detect every second. Trillions of neutrinos pass through your body, originating directly from the stars. These ephemeral particles are generated in nuclear reactions within the Sun, from supernova and from cosmic rays impacting atoms in space. The Milky Way is inundated with them, yet they possess such negligible mass and minimal reactivity that they permeate nearly all matter, leaving no discernible trace. Specialized observatories, deeply situated underground or beneath ice, endeavor to capture even a few of these elusive particles. Flashes of light from a rare collision. Neutrinos convey information from inaccessible locales, from stellar cores, collapsing giants, and the galaxy's unseen energies. They are the whispers of celestial conflagrations. Interstellar space is not an inert void. It is a tempestuous expanse. Between the stars, space is neither uniform nor quiescent. The interstellar medium, composed of tenuous clouds of gas and dust, is agitated by shock waves, magnetic fields, and stellar motion. Temperatures can fluctuate wildly. Streams of matter collide, intermingle, and fragment. Clouds stretch, fold, and tumble. On a grand scale, this generates a form of turbulence akin to an ocean swirling in slow motion through the galactic disk. Star formation, cosmic rays, and indeed, the evolution of galaxies are all influenced by this restless medium. What appears from afar as serene starlight is, up close, a dynamic, undulating tapestry, sculpted by invisible currents and ancient energies. The galactic halo might harbour rogue planets. Planets are not invariably bound to stars. Some form conventionally and are subsequently expelled from their systems. Others may have never possessed a star in the first place. These are rogue planets, worlds adrift within the galaxy, cold, dark, and solitary. Although their detection is challenging, studies indicate that billions of them may exist in the Milky Way, some even residing in the outer halo where stars are exceedingly scarce. Devoid of light or warmth, they float undetected. Sustained only by their internal heat, they are the orphans of the galaxy, planetary wanderers charting solitary, elongated courses through the interstellar darkness. Magnetic fields dictate the movement of cosmic dust. Interstellar dust, minute particles of carbon and silicon, is propelled not only by gravity but also by the influence of the galaxy's magnetic field. These fields permeate the Milky Way like invisible currents, guiding the trajectory of charged particles and governing the alignment of gas and dust. In certain zones, dust grains spin at high velocities, emitting faint microwave radiation. In others, they align with magnetic field lines, polarizing the starlight that traverses them. Comprehending these phenomena aids astronomers in delineating the magnetic field structure and even in mitigating its impact on cosmic background radiation studies. Dust is not passive. It dances to a magnetic cadence, revealing hidden patterns within the darkness. Certain stars are enriched by the remnants of neutron star collisions. When two neutron stars spiral into each other and collide, they instigate one of the universe's most violent phenomena, a kilonova. In this brief, incandescent explosion, prodigious quantities of heavy elements are synthesized: gold, platinum, uranium, and more. These materials are dispersed into space, intermingling with gas and ultimately contributing to the formation of new stars. Some stars within the Milky Way bear the chemical signatures of these infrequent events, enriched with elements that could only have originated from such cataclysmic collisions. They are not merely luminous entities, but repositories of ancient cataclysms, incandescent with the residue of stellar wreckage and cosmic alchemy. The Milky Way might possess a hidden bar within a bar. At the galactic core resides a bar of stars, an elongated bridge of light spanning the central bulge. However, deep within that bar, astronomers have detected indications of a second, smaller bar, tilted at a different angle and rotating independently. This internal structure is difficult to observe directly, obscured by dust and distance, yet its gravitational influence is evident in the motion of adjacent stars and gas. Bars of this nature may facilitate the channeling of material toward the supermassive black hole, providing it with sustenance and shaping the dynamics of the galactic center. The Milky Way's core is not a singular simple form. It is a layered, dynamic labyrinth of light and motion. Gaseous inflows feed the galaxy from the cosmic web. The Milky Way does not operate as an isolated system. It draws fresh gas from the intergalactic medium in the form of tenuous streams flowing through the vast cosmic web. These inflows furnish the raw material for the creation of new stars, replenishing what the galaxy gradually expends. Some gas arrives as cold filaments, quietly entering the galactic disk. Other streams descend in hotter, shock-heated forms, radiating intensely in ultraviolet or X-ray light. These unseen rivers sustain the galaxy's growth and evolution, interconnecting it with the broader universe beyond. Even now, the Milky Way draws nourishment from distant reservoirs, sustained by threads of matter spun from the primordial cosmos. Hot gas bubbles form conduits extending from the disk. When aggregations of massive stars undergo supernova explosions, they generate immense cavities within the interstellar medium. These can coalesce into superbubbles, vast pockets of superheated gas that breach the galactic disk and vent into the halo. The result is a form of chimney, a channel through which energy, gas, and magnetic fields escape from the galactic plane. These chimneys regulate the pressure within the interstellar medium, redistribute heavy elements, and contribute to shaping the halo structure. In this manner, the galaxy exhales not only within its disk but through towering columns that convey its energy upwards and outwards into the void. The galaxy emits X-rays originating from ancient stars and black holes. While the Milky Way appears placid in visible light, it radiates intensely across other wavelengths. X-rays stream from its core from collapsed stars and from the perimeters of black holes. White dwarfs and neutron stars in binary systems can siphon matter from their companions, heating it to millions of degrees. Hot gas within the halo also emits faint X-rays, revealing the galaxy's larger skeletal structure. Our eyes cannot perceive this high-energy radiation. However, telescopes like Chandra and XMM Newton depict a vastly different portrait of the galaxy. Not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and concealed radiation. Pulsars serve as cosmic chronometers throughout the Milky Way. When a massive star collapses to form a neutron star, it may continue to spin rapidly and with remarkable precision, emitting beams of radiation that sweep across space. These are pulsars, and some rotate hundreds of times per second, pulsing with regular, measurable rhythms. They are so consistent that astronomers employ them as cosmic timekeepers, tracking their signals to ascertain distances, test theories of gravity, and even search for gravitational waves. Across the Milky Way, pulsars blink serenely, remnants of stellar demise, yet also beacons of astonishing order. They mark time not in minutes or days, but across entire epochs, ticking with steadfast regularity in the silence between stars. Radio waves map the hidden architecture of the galaxy. A significant portion of the Milky Way remains invisible to optical observation, concealed by dust, distance, or faintness. However, radio waves can penetrate these barriers, revealing structures otherwise concealed. They delineate cold hydrogen gas, outline magnetic fields, and highlight emissions from pulsars, supernova remnants, and even distant quasars beyond the galaxy. Utilizing arrays of radio telescopes, astronomers have charted the spiral arms, measured the galactic disk's warp, and discovered star-forming regions cloaked in darkness. Where visible light is obstructed, radio soundings enable us to perceive. The galaxy communicates in a language we cannot audibly comprehend, yet one that science has learned to translate into form and shadow. The Sun was likely born within a stellar cluster. Stars seldom originate in isolation. They are typically born in groups, stellar clusters formed from the same collapsing cloud of gas and dust. Our Sun was almost certainly one of these. Eons ago, it shared its environment with hundreds, perhaps thousands of sibling stars, all born from the same stellar nursery. Over time, gravitational tides, passing stars, and galactic motion dispersed the cluster. Most of the Sun's siblings have drifted far apart, flung into different orbits, carrying with them fragments of their shared past. Some may still shine nearby, indistinguishable among the multitude of stars, lost family members within a sea of light. The Sun's siblings are scattered throughout the galaxy. Although the Sun's natal cluster has long since disintegrated, astronomers are actively searching for its dispersed siblings, stars that share its age, orbital characteristics, and chemical composition. Employing extensive surveys like Gaia and spectroscopic databases, researchers aim to identify these long-lost relatives. Several candidates have emerged, stars that may have originated from the same cloud of enriched gas. If confirmed, they could illuminate the conditions under which the Sun and the early solar system came into being. Our position within the galaxy is not entirely solitary. Somewhere out there, the Sun's ancient kin may still twinkle. The galactic disk exhibits a wobble as it rotates. The Milky Way's disk is not perfectly planar. It oscillates gently, rippling like a spinning platter nudged off its equilibrium. This warp is most pronounced in the outer regions, where the disk curves upward on one side and downward on the other. It may be attributed to the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries. The wobble propagates slowly, like a vast wave traversing the stellar population. From our vantage point on Earth, we do not perceive it. However, viewed from a distance, the Milky Way is not a pristine spiral. It is a dynamic, undulating sheet of stars, curving gracefully as it turns. Galactic tides can distort star clusters and streams. Just as the Moon's gravity induces tides on Earth, the immense mass of the Milky Way exerts tidal forces on all objects within its influence. Star clusters, satellite galaxies, and even globular groupings feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, elongating them into vast stellar streams or dislodging stars from their orbits. Many of the faint arcs of stars mapped across the sky are remnants of such interactions. Clusters undergoing this process are being unravelled. Galaxies are slowly torn apart. The galaxy does not dismantle these structures abruptly. It unravels them patiently, strand by strand, over millions of years. The mass of the Milky Way remains uncertain. One might assume we would possess a precise measurement of our own galaxy's mass, yet determining it is remarkably challenging. Stars and gas constitute only a small fraction of the total mass. The remainder resides within the vast dark matter halo, which we cannot directly observe. Estimates vary. Some suggest a mass approaching 1 trillion times that of the Sun. Others place it considerably higher. The uncertainty stems from the difficulty of measuring stellar orbital velocities at great distances, a task complicated by limited data and the pervasive influence of unseen matter. The Milky Way is our home, yet its total weight remains an unresolved enigma. It may be more massive than Andromeda. For many years, astronomers presumed that the Andromeda galaxy, slightly larger and brighter than the Milky Way, was also more massive. However, recent measurements indicate that the Milky Way's dark matter halo might be more extensive and denser than previously believed. If this is the case, our galaxy could outweigh Andromeda, despite its more modest outward appearance. This consideration is crucial not only for comparative analyses but also for predictive modelling. When the two galaxies eventually merge, their relative masses will dictate the dynamics of the encounter. The Milky Way may appear gentle, but beneath its serene spiral arms, it carries more gravitational heft than we once imagined. The Magellanic Clouds might be on their initial orbit. The Large and Small Magellanic Clouds, two prominent satellite galaxies observable from the southern hemisphere, have long been considered to orbit the Milky Way. However, recent evidence suggests they may be newcomers, captured only recently in cosmic terms. Their velocity and trajectory through space indicate that this could be their first close approach. If so, they are not long-standing companions but distant wanderers newly drawn under the Milky Way's gravitational sway. Their arrival has perturbed the outer disk and distorted the galaxy's shape. It is as if the Milky Way is reacting to a new gravitational visitor, with the celestial sphere alive with first encounters. The Magellanic Stream is a ribbon of stripped gas. Trailing behind the Magellanic Clouds is an immense ribbon of hydrogen gas, a formation known as the Magellanic Stream. It extends for hundreds of thousands of light years, forming curves and arcs across the southern sky. This stream was drawn out by tidal forces as the dwarf galaxies passed in close proximity to one another and to the Milky Way. Invisible in optical light, it reveals itself through radio wavelengths, a long trailing whisper of motion and loss. The stream may eventually contribute to new star formation within the Milky Way, or settle into the halo, resembling a thread of memory stretching between galaxies. Some gas clouds orbit in polar orientations. Not all matter within the Milky Way adheres to the planar structure of the disk. Certain clouds of gas, and even some stars, traverse highly inclined orbits, passing above and below the galaxy's primary structure. These polar orbits likely result from past mergers, wherein dwarf galaxies or stray clouds were captured at oblique angles. Over time, they continue to orbit on tilted paths, akin to comets around a planet. These misaligned orbits are testaments to past disruptions, visible reminders that the galaxy is not a self-contained entity, but an evolving structure shaped by the unpredictable currents of cosmic history. Giant shells of gas encircle past starburst events. In several regions of the Milky Way, astronomers have discovered colossal spherical shells of gas, some spanning hundreds of light years. These shells are the remnants of powerful starbursts, periods when dense clusters of massive stars formed simultaneously, lived brief, incandescent lives, and exploded in rapid succession. Their collective stellar winds and supernova explosions carved immense cavities within the interstellar medium, expelling gas outwards in all directions. As time progresses, the expansion diminishes, but the shells endure. Ghostly bubbles marking locations where the galaxy once blazed with stellar birth and death. These are the fossils of celestial fireworks, their echoes still resonating in the cold vacuum. Stars occasionally collide in dense environments. Space is vast and stars are diminutive. However, in the most densely populated regions of the Milky Way, such as the cores of globular clusters, stars can approach close enough to interact and even collide. When this occurs, the outcome can be dramatic. A surge of light, the merging of two stellar bodies, or the formation of a rare blue straggler star, appearing younger than its neighbours. These collisions are infrequent but not impossible. Over billions of years, the most tightly packed stellar neighbourhoods can be reconfigured through the interplay of gravity and chance. In these crowded stellar metropolises, time progresses differently, and space is never entirely unoccupied. Binary stars can be sundered by tidal forces. Many stars exist in pairs, orbiting each other in a gravitational embrace. However, even this bond can be severed. If a binary system passes in close proximity to the Milky Way's central black hole, or traverses a dense stellar cluster, tidal forces can disrupt their orbit, flinging one star away while the other is captured or decelerated. In some instances, a companion star is expelled from the galaxy entirely, becoming a rogue star hurtling through intergalactic space. These stellar separations occur silently in obscure locations, a quiet rending of ancient partnerships by the inexorable hand of gravity. Some stars escape the galaxy entirely. The majority of stars are gravitationally bound to the Milky Way, but occasionally a star achieves escape velocity over 500 kilometers per second and is ejected outwards, never to return. These hypervelocity stars are rare but demonstrably real. Some are thought to be propelled by interactions with the supermassive black hole at the galaxy's centre. Others may be slingshotted by three-body encounters or by supernova explosions within binary systems. Once liberated, they journey alone into intergalactic space, tiny beacons drifting far beyond the spiral's edge. They carry the galaxy's memory outwards, becoming solitary pilgrims in the vast darkness between galaxies. The Milky Way contains stars originating from other galaxies. Not all stars within the Milky Way were born within it. Some may have originated in different galaxies, captured during mergers, or ejected into our halo from distant regions of the local group. These intergalactic wanderers often follow unusual orbits far from the galactic disk, tracing paths through the outskirts or halo. They can be identified by their elemental composition or their motion, stars that do not quite conform to local patterns. Like cosmic immigrants, they bring narratives from different environments, distinct histories, and alien skies. The Milky Way is not an isolated system. It is a living mosaic, gradually stitched together by time and motion. Acting as a fountain of gas cycling between the disk and halo, above and below the Milky Way's luminous disk, gas ascends and descends in a silent loop known as the galactic fountain. Supernovae and stellar outflows propel material upwards into the halo, where it cools, coalesces, and gently descends over eons. This ongoing process agitates the interstellar medium, redistributes heavier elements, and influences the genesis of stars. It represents a silent respiration, a cosmic exchange of matter between the dense galactic plane and its expansive halo. Consequently, the galaxy doesn't merely rotate, it circulates, breathing in and out, maintaining its form through immense stretches of time. Within the nebulous clouds of interstellar dust that drift between stellar bodies, scientists have identified intricate organic molecules, carbon-based compounds that serve as fundamental precursors to life. These include polycyclic aromatic hydrocarbons, rudimentary sugars, alcohols, and more. Though inert, they are chemically abundant, synthesized in the envelopes of expiring stars or within frigid nebulae shaped by energetic radiation. These microscopic particles, transported across vast interstellar distances by galactic currents, settle into the gaseous material that coalesces into stars and planetary bodies. It is conceivable that some may have reached early Earth. The galaxy's dust is not mere detritus, it is a payload of potential, silently traversing the void. Stellar nurseries also act as harbingers of life's building blocks. The very locations where stars ignite are also the cradles of worlds. As planetary systems assemble from collapsing clouds of gas and dust, they absorb the unique chemical signatures of their parent nebulae. Should such a cloud harbour water, carbon compounds, and other biological precursors, these constituents may ultimately be incorporated into comets, asteroids, or planets. Certain sectors of the Milky Way are particularly replete with such prebiotic chemistry. The prevalence of life remains an enigma, yet the conditions necessary for its emergence appear to arise spontaneously. The genesis of life may be disseminated broadly, nestled within the galaxy's coldest cradles, awaiting an opportune environment for development. While the Sun completes a rotation in 25 to 35 days, depending on its latitude, certain stars rotate at speeds hundreds of times greater, completing a full revolution in mere hours. These rapid rotators are often nascent, massive, and inherently unstable, their equatorial regions distended by centrifugal forces. A few achieve such extraordinary velocities that they expel matter, forming incandescent disks around themselves. Their internal architectures and evolutionary trajectories diverge significantly. Though their lifespans may be abbreviated, they spin with a captivating intensity throughout their existence. The Milky Way's plane is not aligned with the ecliptic. From our terrestrial vantage point, the Milky Way traces an elegant luminous arc across the nocturnal firmament, yet it does not coincide with the orbital path of our solar system. The galactic plane, the flattened disk containing the majority of the galaxy's stars, is inclined at an angle of approximately 60 degrees relative to the ecliptic, the trajectory followed by the Sun and planets. This inclination accounts for the Milky Way's elevated angle of appearance and its shifting position throughout the seasons. We are integral to the galaxy, but our localized system is slightly askew, akin to a small, tilted vessel navigating a vast, rotating celestial sea. Among the faint luminaries in the halo, astronomers have discovered white dwarfs, the cooling remnants of once brilliant stars, which predate the Milky Way's thin disk itself. These ancient vestiges formed when the galaxy was in its infancy, prior to the full stabilization of its primary structure. Their presence suggests an earlier epoch of stellar genesis, a more profound history inscribed within the outer halo. These have endured for billions of years, gradually fading, bearing the quiet legacy of a time when the Milky Way was still coalescing. The disk may be luminous, but the halo retains memory of an even earlier era. The Milky Way's most remote stars traverse orbits far beyond the familiar spiral arms, extending tens or even hundreds of thousands of light-years from its core. These stars journey through the galactic halo along slow, sweeping paths, requiring billions of years for a single revolution. Many were likely absorbed from smaller galaxies during past collisions, now residing in the outermost expanses like distant sentinels. Though faint, sparse, and widely separated, they help delineate the galaxy's dimensions, configuration, and gravitational influence. The Milky Way encompasses more than what is readily observable. It extends far into the darkness, its form shaped by wanderers at its periphery. Although frequently depicted as a symmetrical spiral, the Milky Way exhibits subtle asymmetries. One side of its disk is perceptibly thicker than the other. The spiral arms vary in luminosity and extent. Even the stellar halo is marginally off-center. These discrepancies likely stem from gravitational interactions with dark matter concentrations or from prior galactic mergers. The galaxy is not a perfectly uniform disk. It is a dynamic entity, subject to pulls and twists. much like a spinning performer whose skirt is caught by a gust of wind. Its aesthetic lies in this very irregularity, a graceful imprecision sculpted by the passage of time. Certain stars exhibit pulsations in brightness at regular intervals, expanding and contracting like slow, luminous heartbeats. These are known as variable stars, and specific types, such as Cepheids and RR Lyrae, possess well-established correlations between their luminosity and pulsation period. By measuring the duration of a star's brightening and dimming cycle, astronomers can ascertain its intrinsic luminosity and, by comparing this to its apparent brightness, determine its distance. These stars function as cosmic measuring rods, aiding in the charting of the Milky Way's shape, structure, and scale. Launched by the European Space Agency, the Gaia spacecraft is generating the most precise map of the Milky Way ever conceived. By meticulously measuring the positions, movements, and brightness of over 2 billion stars, Gaia is revealing the galaxy's three-dimensional architecture and its temporal evolution. It has identified streams originating from disrupted galaxies, mapped the warping of the disk, and meticulously charted the Sun's orbit. With each subsequent data release, Gaia enhances our comprehension, transforming a hazy stellar expanse into a sharp, dynamic map. It represents astronomy's most ambitious celestial chart, a quiet transformation unfolding among the stars. On a dark, unpolluted night, one might observe a faint, luminous river arcing across the sky. This is the galactic plane, the thickest stratum of the Milky Way's disk. It is not a linear feature, but a volume, a vast flattened band where the majority of the galaxy's stars are situated. Within this plane, stars are densely aggregated, dust layers are present, and star formation is a common occurrence. From our perspective, we're looking along the grain of the galaxy, peering through its most abundant corridors. This luminous band is not merely aesthetically pleasing, it is the bustling, vibrant heart where most stars originate and extinguish. The core of the Milky Way resides in the direction of the constellation Sagittarius, a rich and radiant concentration of stars, dust, and unseen mass. From Earth, direct observation of the very centre in visible light is obstructed by intervening dust clouds. However, the region emits strongly in infrared and radio wavelengths. Even with the naked eye, the area appears more densely populated and luminous, illuminated by the overlapping light of billions of stars. We orbit at a considerable distance from this centre, in a tranquil periphery of the galactic disk. Nevertheless, when we direct our gaze inward, we glimpse the crowded metropolis at the galaxy's core. Because we inhabit its interior, we're unable to view the Milky Way from an external perspective. Instead, we perceive it from within, as a flat ribbon of stars stretching across the sky, its curvature defined solely by the horizon. This internal perspective compresses the galaxy into a singular arc, rendering a comprehensive understanding of its structure challenging from our vantage point. Centuries of observation, cataloguing, and mathematical inference were required to comprehend the spiral we inhabit. From Earth, we look through its disk as one might stand in a forest and gaze along the line of trees. We do not see the overarching form of which we are a part, only the vastness that surrounds us. The galaxy harbours far more than we can ever perceive. Even with our most sensitive instruments, we glimpse only a fraction of the Milky Way's contents. Light is impeded by dust. Motion is masked by silence. Dark matter significantly outnumbers luminous stars. Emptiness exists between every star, and within every void lies potential. It is what we surmise, what we infer, what we yearn to comprehend. It contains ancient light, future stars, drifting worlds, and unanswered questions. And within that immensity, we somehow find ourselves, a single planet among many, orbiting a quiet star, adrift within a narrative too expansive for the eye to grasp. And now, the stars begin to fade behind your contemplation. We have traversed 100 quiet truths, from the warping of the galaxy's disk to the most distant halo stars, from nascent suns to long extinguished remnants, from dust and gas to light and shadow, and all that lies in between. You have wandered through stellar nurseries, danced along spiral arms, and gazed toward the galactic heart, concealed behind veils of dust. You're an integral part of this galaxy, not merely a passenger on Earth, but a participant in its prolonged and brilliant unfolding. The iron in your blood was synthesized within stars. The oxygen you inhale was shaped by ancient cosmic explosions. The atoms composing your body trace their lineage to the earliest epochs, born from the same primordial matter that now fuels suns and whispers through interstellar dust clouds. Tonight, as you rest, the galaxy continues its ceaseless rotation. Stars are forming, light is propagating, silent orbits persist, and you are suspended within it, a small warmth in the darkness, resting in the spiral arm of a tranquil, luminous expanse. If you're still awake, you may proceed to witness the next segment. I hope you enjoy a restful sleep and have gentle dreams. Good night. Thank you. Heat. Thank you. Heat. Heat. What are you doing?